Section 5 is not a particularly interesting one. It's called the extended real number system. Okay, and it's basically, how do you put infinity into the real numbers, right? We'd like to add in a number that we call infinity, right? How do we put that thing in? And the way we do it is sort of unnatural. What we do is we just say, the extended real number system is defined as a set as just the real numbers union two symbols, negative infinity and positive infinity. So we just stick them in there. Okay. We say the extended reals are going to be our normal real numbers, and we're also going to add these two things that we call negative infinity and positive infinity, and we make the extended reals. We make the extended reals an ordered set by one, preserving the original order on R, right? Just use the same old order that we stuck with, that we had at the beginning, and two, defining that negative infinity is less than x for all x, and for all x in R. Let me say it like this. This for all x in R. That every finite number is strictly greater than negative infinity and strictly less than positive infinity. Okay, so the extended real number system is an ordered set. Okay. It's an ordered set. We will not be able to make it into a field. Okay. We will not be able to make it into a field, let alone an ordered field. Okay. Because how are you going to talk about multiplying and dividing by infinity in a way that's consistent with the field axioms? Right? You want to be able to cancel, right? But then how are you going to define 2 times infinity? Is it the same thing as 1 times infinity? If it is, then you should be able to cancel. Right? If it's an ordered field, you should be able to. If it's a field, there should be some inverse element to this, right? There should be some multiplicative inverse to this, but then you run into trouble, right? So the trouble is you can't make it in a field because what's the inverse element? What's the multiplicative inverse of infinity? Right? Normally you don't have something that you multiply infinity by and get 1. I should say that I think there is a way of doing it, but you have to extend your number system to a completely different number system that's given the funny name the serial number system. But we're not going to talk about that. Okay, so a couple of remarks. One, positive infinity is an upper bound of every subset of the extended reals. And similarly, negative infinity is the lower bound for every subset of the extended reals. 2, in the extended reals, every non-empty subset has the least upper bound. Every non-empty subset has a least upper bound. Okay. Previously, we had sets that didn't have least upper bounds, right? Or we had sets that didn't even have upper bounds, right? Like if you look at, the set of all real numbers, well, that doesn't have an upper bound, right, in the real numbers. But now it does, right? Infinity is an upper bound of that set. Right? In fact, infinity is the least upper bound of that set. Okay, so right, every non-empty subset is going to have a least upper bound. Why? Because if S has a finite upper bound, then it has a least upper bound by completeness. If if S has no finite upper bound, then infinity is the least upper bound. Right? Then infinity works as its least upper bound. Okay. There are a bunch of conventions about how infinity should work with, the standard operations of the field. So people usually say that for real numbers, x plus infinity equals infinity, right? X minus infinity equals minus infinity. X divided by plus or minus infinity is set to be 0, right? For positive x, if you multiply by infinity, you get infinity. If you multiply by negative infinity, you get negative infinity. And similarly for negative x, if you multiply by positive infinity, you get negative infinity. You multiply by negative infinity, you get positive infinity. So these are the normal conventions. It's handy for us to have to use the extended real number system, and you'll see why. I think you'll see why later, depending on how far we go. Okay, but in any case, the main thing is that you create the extended real number system by throwing in, you just sort of arbitrarily stuff in negative infinity and positive infinity, and you make it as you expect, right? It's bigger, infinity is bigger than all numbers, and then it does what you sort of expect it to do. Okay. I should say that there are more natural ways of putting infinity into the number system. One cool way, so this, you don't have to know this, but one cool way is what happens in complex analysis. So in complex analysis, you have the complex plane, right? So this is the real axis, this is the imaginary axis, right? And every point on the plane, right, is some combination of real number plus imaginary number. Okay. Another way of thinking about the complex plane is to project it onto a sphere. This is called the Riemann sphere. projection is called stereographic projection. And it has various properties. Okay, and so what you do is you take a unit sphere and you sit it, you put it, you lie the plane down. You put the plane flat, you put a sphere on top here, okay? And you say, every number is going to be identified with a unique point on the sphere, okay? And the way you find that point is you take the North Pole and you draw a ray from the North Pole to that point, and you see where it intersects the sphere. Okay, so like guys who are close by will be, their ray will hit somewhere in the southern hemisphere, right? Points that are far away will hit higher and hidder on the northern hemisphere. Okay, and in this way, every point in the complex plane, this is a C, every point in the complex plane gets identified with a point on the sphere. So the whole sphere, you think of it as the complex plane now. It's the complex sphere of numbers. Okay. Now the funny thing is, you notice is that there's a hole in the sphere, right? There's one point that doesn't get covered. That's this top, the North Pole, right? No point on the plane gets mapped to that North Pole, right? So there's this hole in the point in the top. However, this point on the top, as you see, as you head farther and farther away from the origin, right? Farther and farther away from the origin, you get closer to that point on the top, right? So, right, if we look at, if we take a little disk, if we cut a tiny disk out here, what that turns into is a gigantic circle, right? A gigantic circle in the plane, right? And all the points in here correspond to the guys outside that circle, right? Okay. So generally, you say, okay, we're going to call this thing the whole sphere. We call the complex. We call C unit infinity, where this top guy you think of as infinity, right? Because it sort of has the properties of what you think infinity should be, right? As your numbers become larger and larger, you get closer and closer on the sphere to this point, right? So this is sort of a natural representative of infinity, right? It's something that you would think of, yeah, that's infinity.
So why is there a hole?
Well, every point on the plane gets mapped to a point on the sphere, right? And so now you think every point on the sphere will correspond to a point on the plane, conversely, right? Except for this point up here, right? This point up here doesn't get mapped anywhere on the plane, right? There's no point that just somehow goes straight to the top there, right? It's going to intersect the sphere at some point, right? Just by the curvature, right? It's going to intersect at some point. Okay, so that's actually like probably the most natural way of talking about what infinity is.
It's cool.
Yeah. There's a cool book called Visual Complex Analysis. Visual Complex Analysis by Tristan. That's sort of complex analysis in a way that people don't usually see complex analysis. And I think he's a physicist. So he ties it back to physical things in physics. Yeah, it's fun reading, although very different from how people would normally teach complex analysis. Like I wouldn't teach complex analysis in this way, but maybe it should be taught in that way. It's very interesting. Okay, let's go on. Okay, so we're going to skip section 6 because it's about the construction of the real numbers. Instead, we're going to go on to section 7, the rigorous definition of the limit. Okay. And I should say that this is a really crucial definition in analysis. And the kind of arguments that we're going to be doing here are basically, bread and butter type arguments in analysis. Okay, so this is what we're going to do for the next 2 sections is really fundamental stuff. Okay. If you can do this stuff, then you'll be comfortable with the analytical stuff. Okay, so make sure you get it. Okay, so we're going to define initially, at least, limits for sequences. And maybe you've seen this before, so let's get to it. So a sequence, I'm sure you've all seen this stuff. A sequence is a real valued function whose domain is of the form integers where you start off from some, where m is some fixed integer. Okay, so for example, right, if I say, here's my function, a of n is 1 plus 1 over n to the n, where n starts at 1. Okay, so this is a sequence. Okay. This is a sequence, right? Its first element, right, is 1 plus 1 to the 1, right? 1 plus 1 to the 1. Its second element is 1 plus 1/2 squared. Its third element is 1 plus a third cubed, etc., etc. Right? Maybe you know where the sequence is going to go. What's the limit? What does the sequence go to in the end?
1?
No?
2?
No? E. Right. So this is a sequence. This is starting at 1. We said it could start at any fixed integer, right? So if I started from 10, that's also a sequence. It doesn't matter, right? Sequences can start at some integer. Okay. Example 2. Let S sub n be defined as the sum of 1 over n squared as n goes from 1 to, k squared as k goes from 1 to n. And n again is going to be 1, 2, 3, etc. Can you rewrite this? It's so ugly. Okay. So, right, S1 is going to be the sum of the reciprocals of squares from 1 to 1, right? So it's going to be 1 over 1 squared. S2 is going to be 1 over 1 squared plus 1 over 2 squared. S3 is going to be 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared. Right? So it's the sum of reciprocals of squares, right? Up to that nth element. Okay. Does anybody know what this sequence tends to?
0.
0? No? Because you start from 1 and then you keep on adding more. This is 1 plus a fourth, 1 plus a fourth plus a ninth.
Infinity?
2? No. The answer is I squared over 6.
Obviously.
Yeah, but you won't see the proof of that for some time. Okay. Okay. Another example?
So we'll have to prove that?
No, you will not. see or be able to prove it for
Okay.
at least for a short while. Right? I think if you take 131, actually, that
What is 130?
the course that actually this prepares you for,
Oh.
right? So this is like Introduction to Real Analysis, Introduction to Analysis, and that course is Principles of Analysis. Yeah. So if they use Rudin's book, this is actually a problem in Rudin's book. Although when we did it, I think the TA said that it was not possible. Like he said, I'm sorry, actually this problem was not possible for you. But I don't know if that's true. Okay, so so another example, -1 to the n. -1 to the n. Right. So the first guy is -1. The second guy is -1 squared. The third guy is -1 cubed, etc., etc. Right. You see that. Oops. You get these numbers that bounce back and forth between -1 and 1. Okay, and it doesn't tend towards anything. Okay, so remark that one usually notates elements of a sequence with subscripts, not parentheses. So for example, these guys, the A of n, usually we write A sub n, S sub n, F sub n. Right? You don't write, this would, normally you'd write this as A sub 1, this guy would be A sub 2, A sub 3, not A of. You hide that it's a function. You hide that it's a function. You make it look more like a sequence. Okay. And when notates the full sequence as this sort of thing, right? The set of S sub n, the set of A sub n as n goes from 1 to infinity, right? Or some people use this notation, use a bracket. Okay. So just to give you the sequence notation, next time we'll talk about what it means to talk about limits. Okay, the limit of a sequence, the formal definition of that. The idea and the definition. Okay. Yes?
Did you say n is greater than or equal to z?
Oh, what am I doing?
Subset of z, right? Element of z.
Yeah, thank you. Okay, that's it for today.